Good day and welcome to our today's class on the monotone convergence theorem, which is also called MCT. The theorem concerns convergent sequences that are both monotone and bounded. And the theorem states that a monotone sequence of real number is convergent if and only if it is bounded. If and only if it is bounded. Another way of stating the theorem is to state that what? Every bounded monotonic sequence, every bounded monotonic sequence is convergent or has a limit. That's another way of stating the monotonic sequence. When we look at the first one, which we want to concern ourselves with, that is a monotone sequence of real number is convergent if and only if it is bounded. Because of the presence of this if and only if, it tells us that it is a two-way proof, a two-direction proof. And what is the first direction of the proof? The first direction of the proof, we mean that we want to show that if a monotone sequence is bounded, if a monotone sequence is bounded, then it is convergent. Then it will be convergent. And the second direction of the proof will be to show that if a monotone sequence is convergent, then it is bounded. So we begin by proving the first direction. First direction. If a monotone sequence is bounded, then it is convergent. That's the first one we want to prove. Now, for us to prove that, recall the definition of monotone sequence. A monotone sequence, or a sequence, is said to be monotone if it is either increasing or decreasing. Therefore, a monotone sequence is a sequence that is either increasing or decreasing. So when we are talking about monotone sequence, it means we are looking at increasing or decreasing sequence. Also, by definition of bounded sequence, a sequence is bounded if it has a lower bound. Also, by definition, a sequence is bounded if it has both a lower bound and an upper bound. If it has both a lower bound and an upper bound. Now we want to assume that we are working with an increasing and bounded sequence. Now our assumption. Let an be an increasing and bounded sequence. Let an be an increasing and bounded sequence. You want to show for a monotone increasing, let an, a sub n, be a monotone increasing and bounded sequence. Now, if a sub n is bounded, this is an increasing sequence, it means that a sub n has an upper bound. This implies that the sequence a sub n has an upper bound. And this further implies that the sequence A sub n has a supremum. A supremum. That is, it has a least upper bound. Therefore, let alpha be the supremum of A sub n for all n belonging to the set of natural numbers. We want to show that A sub n, we want to prove that A sub n is convergent. That is, the limit as n tends to infinity of A sub n equals infinity. By definition of supremum, it means that for all epsilon greater than 0, there exists a I in this belonging to the set of natural numbers such that alpha minus epsilon is less than A sub I. Assuming I is less than or equal to n, which is the same thing as n being greater than or equal to I. Therefore, alpha minus epsilon is less than A sub I, which is also less than what? Which will be less than A sub n, since I is less than or equal to n for all n belonging to the set of natural numbers. But A sub n will be less than the supremum of A sub n. But A sub n is less than alpha. Therefore, alpha minus epsilon is less than or equal to A sub I, which is less than or equal to A sub n, which is less than or equal to the supremum. Moving ahead from there, alpha minus epsilon is less than or equal to A sub I, which is less than or equal to A sub n, which is less than or equal to alpha, which definitely will be less than or equal to alpha plus epsilon. And that implies that alpha minus epsilon is less than or equal to A sub n, less than or equal to alpha plus epsilon. Subtract alpha all through. We have that what? Minus epsilon will be less than or equal to A sub n minus alpha, which is less than or equal to epsilon. By equivalence now, the absolute value of A sub n minus alpha will be less than or equal to epsilon for all n greater than or equal to k. Therefore, the sequence A sub n converges to alpha, and that implies that the limit as n tends to infinity of A sub n equals alpha. Therefore, a monotone increasing and bounded sequence is convergent. Remember, we are still proving the first direction of the monotone convergence theorem, which says a monotone, if a sequence is monotone and bounded, then it is convergent. We have seen for a monotone increasing and bounded sequence. How about a monotone decreasing and bounded? Now, let an, that's the second aspect of the first direction, let the sequence A sub n be a monotone decreasing and bounded sequence. What do we want to show? We want to prove that it is also convergent. But since it is a decreasing sequence, it means that what? A sub n has a lower bound. It means that A sub n has a lower bound. And if A sub n has a lower bound, it further implies that the sequence A sub n has an infimum, which we also call the greatest lower bound. Now let beta be the infimum of a sub n for all n belonging to the set of natural numbers. Let beta be the infimum. Then it means that what? By definition of infimum, therefore, by definition of infimum now again, it means that for all epsilon greater than 0, there exists a I belonging to natural numbers such that beta plus epsilon will be greater than a sub I. Beta plus epsilon will be greater than a sub I. That implies that a sub I will be less than beta plus epsilon. But assume that I is less than or equal, is greater than, since it's an increasing sequence, a decreasing sequence. Assume that I is greater than or equal to n. It implies that n is less than or equal to I. Therefore, a sub n will be less than or equal to a sub I, which is less than or equal to beta plus epsilon. But a sub n will be greater than the greatest lower bound. Yes, the infimum. A sub n will be greater than the infimum. And that implies that the infimum is less than a sub n. Therefore, beta will be less than a sub n, which is less than a sub I, which is also less than or equal to beta plus epsilon. If we subtract anything from beta, it will be less than beta. And that further implies that beta minus epsilon will be less than or equal to beta, will be less than or equal to a sub n, will be less than or equal to a sub I, will be less than or equal to what? Beta plus epsilon. We can shrink this, and we have beta minus epsilon to be less than or equal to a sub n, less than or equal to beta plus epsilon. Again, we subtract beta all through. We have what? Minus epsilon to be less than or equal to a sub n minus beta to be less than or equal to epsilon. By equivalence, again, we have the absolute value of a sub n minus beta to be less than or equal to epsilon. Therefore, if a sub n is monotone, decreasing, and bounded, as we initially assumed, therefore, monotone, decreasing, and bounded, then it is convergent. And so we have been able to prove the first direction of the MCT, which says if a sequence is monotone and bounded, then it is convergent. Then it is convergent. That's the first direction of the closing. Now we want to prove the second direction of the monotone convergence theorem. We want to prove the second direction of the monotone convergence theorem. It says if a monotone sequence is convergent, then it is bounded. If a monotone sequence is convergent, then it is bounded. To prove this, we will prove it using the contrapositive. We are going to prove using the contrapositive. But what is the contrapositive? Let's look at the statement of the theorem of the second direction. It says monotone sequence convergent implies, or then it is bounded. If this is our statement Q, then Q implies P, statement P. Now the contrapositive will be not Q implies not P. Therefore, if a monotone sequence is not convergent, meaning that it diverges, is divergent, then it is unbounded. That's the contrapositive. And it's the same thing as saying if a monotone sequence is unbounded, then it is divergent. That's what we want to prove now. Let's go ahead and see how the proof works, or how to prove the contrapositive. Let a sub n, since it is monotone, remember we have said it can either be increasing or decreasing. Let a sub n be a monotone increasing and unbounded sequence. We want to prove that it diverges. We want to prove that an diverges. For us to prove that it diverges, let us recall the definition of divergence. Let us recall the definition of divergence. By definition of divergence, by definition of divergence, by definition of divergence, a sequence diverges to positive infinity if and only if for any n greater than 0, there exists a k belonging to n such that if n is greater than k, then a sub n will be greater than n. A sub n will be greater than n. But since an is monotone increasing, since sequence a sub n is monotone increasing, it implies that a1 is less than a2, is less than a3, down, is less than a sub n, less than a sub n plus 1, and it continues like that. This implies that the first term of the sequence is the lower bound for the sequence, but it does not have an upper bound. That is why it is unbounded. So we want to show that it diverges to positive infinity. Let's take n to be greater than 0, and let I be less than n. This implies that what? A sub I will be less than a sub n, which is less than a sub n plus 1, less than a sub n plus 2, and it continues like that. And therefore, there exists a m that is greater than a sub, that is less than, there exists a m that is less than a sub I. And since a sub I is less than a sub n, therefore n is less than a sub I less than a sub n, and that implies that n is less than a sub n. Therefore, a sub n is greater than n for all n greater than I. And that implies that the sequence a sub n diverges to positive infinity. Therefore, if a monotone increasing sequence is unbounded, then it diverges. That is, it does not converge. We have shown that for monotone increasing sequence. How about a monotone decreasing sequence that is unbounded? Again, let a sub n be a monotone decreasing sequence that is unbounded. We want to prove that it also diverges. We want to show that A sub n diverges. Since A sub n is decreasing, it implies that A1 will be greater than A2 greater than A3, down, 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 greater than A sub n, greater than A sub n plus 1, greater than A sub n plus 2, and it continues like that. Since A sub n is decreasing, we want to show that A sub n diverges to negative infinity. By definition of divergence, a sequence diverges to negative infinity if and only if for any m less than 0, there exists a k belonging to the set of natural numbers such that if n is greater than k, then A sub n will be less than n. We have said we want to take n to be less than 0 and let I, as we have seen here, be greater than n. Let I be greater than n. This implies that A sub I will be greater than A sub n, and A sub n is greater than A sub n plus 1, greater than A sub n plus 2, and the sequence continues like that. There exists a m that will be greater than A sub I, and that means that what? M is greater than A sub I greater than A sub n. Our m is greater than A sub n. And this implies that A sub n is less than m. Therefore, the sequence A sub n diverges to negative infinity. And so from there, we have been able to prove the second direction of the monotone convergence sequence, which shows us that an increasing and unbounded sequence diverges to positive infinity, and a decreasing and unbounded sequence diverges to negative infinity. Therefore, a monotone unbounded sequence diverges. But we have proved the first direction before, which says that what? A monotone sequence is bounded if it is convergent. And therefore, that is the proof for our monotone convergence theorem. If you have gained anything from today's proof, give it a thumbs up, like it, share it with your friends and colleagues. Thank you. God bless you. I see you in the next video.